What's up, everybody? Welcome to the fourth lecture. This will be over the second part of section 1.6. It's going to be talking about this idea of the one-sided limit. One-sided limits take two different forms, a limit from the left and a limit from the right. And we denote the difference between the two simply by saying the limit as x approaches some value from the left of f of x. Or the limit as my mistake, the limit as x approaches c from the right of f of x. So the distinction in the notation here is just a superscript negative sign to mean we're coming from the left, or a superscript positive sign to mean we're coming from the right. And just to kind of show what this looks like, and to give an intuitive understanding of what's happening here, we could look at the function, the absolute value of x divided by x. If we were to consider the limit from the left over here. So this is the limit as x approaches 0 from the left of f of x. Well, as we approach 0 from the left, so from over here, our value, our function, just approaches -1, right? It's a constant for anything to the left of 0. So as we get closer to 0, we're just getting -1 back. That's all. So coming from the left, our function approaches -1. Now, coming from the right, things change a little bit, right? Because coming from the right, our function is going to approach 1. So we would write that, use a different color, we would write that the limit as x approaches 0 from the right of f of x is equal to 1. Now, in a situation like this, where the limit from the left and the limit from the right don't agree, we would say that the limit as x approaches 0 does not exist. So you can have one-sided limits and not the limit. So there's a distinction here, right? The distinction is, when we're talking about the one-sided limits, we're literally just talking about one case. Does our function have a limit coming from the left? Does our function have a limit coming from the right? But when we talk about the limit, not the one-sided limit, just the limit, that requires both cases to be true. And that's what we're saying over here. That if the limit of a function from the left is equal to L, and that is the same value that the limit of your function is from the right, well, if this is the case, so if your one-sided limits agree, then the limit exists, and moreover, the limit then is going to be L. So the limit's got a little bit of nuance to it, right? Because it requires two things to be true and equal, equivalent. It requires the left limit and the right limit both to exist and to be equal to each other. And in that case, we say the limit is equal to that value. Now, I think right now would be a good time just to explain how I knew that this was the graph of the absolute value of x over x. And I think this is a particularly good problem just to get into some of the machinery we're going to use throughout this class, because I personally love to use absolute values in my problems. I think I should take the time to actually explain what the absolute value is. Because up until now, we're typically just told that the absolute value removes any signs. Just makes everything positive. But that's not entirely true. The absolute value of x is equal to the piecewise equation x if x is greater than 0. It's equal to 0 if x is equal to 0. And it's equal to negative x if x is less than 0. So now, when we put it together with this, this is telling us this is equal to x over x does not exist, and negative x over x. So, like I said, taking this absolute value of x now, what we know it to be, and applying it to this problem. Well, the absolute value of x over x is going to be like x divided by x whenever x is greater than 0. It's not going to exist whenever x is equal to 0 because you have a 0 in the denominator. And whenever x is less than 0, well, that's going to be like negative x over x. Well, that just means then this thing is going to come out to be 1 does not exist, or negative 1 accordingly, right? And that's how we can see that the function absolute value of x over x is going to look like this. Now some other notation to be aware of. You'll notice, or at least I hope you can tell on your monitor, you might need to enlarge the video. But you'll notice in this graph, I use open circles at the end of the lines when x is equal to 0. That's to denote the fact that there is no value there. This is like saying we can get as close as we want to x equal to 0 from the right, but we can't get to x equal to 0 from the right. And we can get as close as we want to x equal to 0 from the left, but we can't get to x equal to 0 from the left. So we just leave that as a hole, right? If we had a value there, we would just fill in the holes or have a single dot to represent the value, right? But in this case, because our function does not exist at x equal to 0, well, we don't have a dot to fill in. They're just both holes with nothing else. Having said all of that, let's actually look at how to solve this algebraically now. So we just showed graphically that the limit from the left and the limit from the right are -1 and 1 respectively. We saw that graphically. But if we wanted to see that algebraically, what we would do now is we'd say, all right, cool. We know what the absolute value of x over x is. So the limit as x approaches 0 from the left of the absolute value of x divided by x is equal to, well, the left-hand case is this bottom case down here, right? These are all the values left of 0, less than 0, right? So this has to come out to be -1. Whereas, on the other hand, if we were to take the limit as x approaches 0 from the right, and that's going to come out to be 1. And we can see that because what we've got up here is all of the values greater than 0, so the values to the right of 0, they all spit out a 1. So from the right, our function is equal to, or our limit is equal to 1. And from the left, our limit is equal to -1. And this is how we would play with these. We would break them up into the cases. We would look at them individually, right? Sometimes it's even more simple than that. Sometimes we might have a function like, let me write this out. Let's say we have the function x squared. Well, the limit as x approaches 2 from the left of x squared, that's just going to be 4, isn't it? And the limit from the right well, that's going to end up being 4 as well. And since these two things are equal, we can say that the limit as x approaches 2 of x squared is equal to 4. But we can only say that because the limit from the left and the limit from the right are equal. So let's check out some more problems. Let's look into some of this stuff. So as an example problem, let's consider this piecewise function here. For all of the x values to the left of 1, we've got that our function is equal to 4 minus x. And for all of the x values to the right of 1, we've got that our function is equal to 4x minus x squared. And we want to show that if the limit as x approaches 1 of our function exists. Now, like we just saw a second ago, that means we need to show the limit from the left and the limit from the right as x approaches 1 are either equal or not equal, right? If they're equal, then we can say the limit exists. If they're not equal, then we can say the limit does not exist. So how are we going to do that? Well, we're going to start by taking the limit from the left, the limit as x approaches 1 from the left of f of x is equal to, well, the limit of this function from the left just means we need to take the left-hand side of things, right? Well, everything to the left of 1, our function is going to be equal to 4 minus x. So if we're just looking at the values to the left of 1, this piecewise function is saying everything to the left of 1 is equal to 4 minus x. So this is like the limit as x approaches 1 from the left of 4 minus x. Well, that's a polynomial. So we can just plug in 1. That's what the rules were telling us the last video, right? So if that's the case, then this is just going to come out to be 4 minus 1, or just 3. Huh. Okay. Well, now we need to show it from the right. Doing the same thing, but from the right, we're going to have the limit as x approaches 1 from the right of our function is is equal to the limit as x approaches 1 from the right. Well, now in this case, since we're looking at all of the values to the right of 1, our function, for all of the values of x to the right of 1, our function for all of those values is equal to 4x minus x squared. So this is like saying the limit as x approaches 1 from the right of 4x minus x squared. Well, hey, again, this is just a polynomial, so we can just plug in 1. And when we do that, we get 4 times 1, or just 4, minus 1 squared, which is just 1, and it comes out to be 3. So what this means then is that the limit from the left and the limit from the right are equal to each other, right? So since the limit from the left and the limit from the right are equal to each other, that tells us that the limit as x approaches 1 of our function is equal to whatever that value is. And in our case, it's 3. And voila, that's it. Cool. Let's keep chugging along then. Now, as another example, we've got the function equal to 3 divided by the quantity x minus 2. We want to know if the limit as x approaches 2 of our function exists. Well, let's consider this for a moment graphically. I think that'll be the easiest way to look at this. If we were to look at the graph of this thing, it would look like that. You notice, coming from the left, as we approach 2, right here, our function looks like it just goes down forever, right? As we keep approaching 2 from the left, our function here just goes down forever. In fact, it does. It never ends. It just goes on and on and on forever to negative infinity. So we would say the limit as x approaches 2 from the left is equal to negative infinity. On the other hand, coming at it from the right, well, here we're just going to go up forever. And we're never going to end. Just going to keep going and going and going. So we would say that the limit as x approaches 2 from the right is equal to infinity. Well, I don't know about you, but that doesn't look equal. I don't think that looks equal, right? Negative infinity and infinity, they're not equivalent values. So the limit from the left and the limit from the right aren't equal. And as a result, we would say that the limit as x approaches 2 of our function does not exist. This is generally all I have to show y'all, to tell y'all about this lecture, this section 16B stuff. If y'all have any questions, by all means, reach out. But I think I'm going to leave it here. Have a good one, everyone.